Math 287, Cuesta College. I'm Joe Vesta, and this lecture is section 7.5, Orthogonal Matrices. This is our very last section of linear algebra, and then we move over to differential equations for the rest of this class. So problem number 1. I give you a 2x2 matrix and I ask you if the matrix is orthogonal. Now we've heard that word, orthogonal, and we've done orthogonal vectors and orthogonal sets of vectors, but now we need to define what an orthogonal matrix is, and that's what we're going to do before we do this problem. Let A be an n by n matrix. So we have a square matrix. A is orthogonal if A inverse equals A transpose. So all this is a definition. Why they use the word orthogonal, we will see. So is A orthogonal? So what are they doing? They're actually asking us, does A inverse equal A transpose? And I know what a lot of you are thinking. I mean, you're sick of linear algebra probably, and you're like, who cares? Well, that's not going to be the answer, but I can understand. There's a better way of dealing with this, and it would be this right over here. So let's take a look at this equation here. We have A inverse equals A transpose. I'm going to multiply both sides of that equation by A on the right-hand side. So what is A inverse A? Well, that happens to be the identity. And then this is A transpose A. Now, why would I do that? The reason I would do that is so I could rewrite this question and I wouldn't have to compute A inverse. I don't want to compute A inverse, even if it's a 2x2. I don't feel like doing that. So here's another way of asking that question. Does A transpose A equal the identity matrix? I2 in this case. And so that's the way I'm going to do this problem. Now you can do the problem the other way and compute A transpose and compute A inverse and see if they're equal, but I don't feel like doing A inverse. And if it was a 3x3 matrix, I'm pretty sure I wouldn't want to do that, and I'd like to do it this way. So let's go ahead and crank this out here. A transpose A. Now A transpose is not that hard to do. I'm just going to write the first row as a column. So this is 1 over root 2, 1 over root 2. Okay, so that was the first row. It's the column. And now the second row is the second column. This is negative 1 over root 2, 1 over root 2. A transpose is a lot easier than writing out A inverse. And now A is just this matrix, so we just write the same thing. 1 over root 2, 1 over root 2, negative 1 over root 2, 1 over root 2. Okay, let's multiply that out, see what we get. Well, we have 1 over root 2 times 1 over root 2 is 1/2. 1/2, and then this is going to be plus 1/2 is 1. 1/2 minus 1/2 is 0. 1/2 minus 1/2 is 0. 1/2 plus 1/2 is 1. So guess what? We ended up getting the identity. This is true. Does that equal that? The answer is yes. Yes to the original question as well. Is A orthogonal? The answer is yes. Okay. Well, what do we have? We have a theorem about an orthogonal matrix. And here's the theorem. It says A is orthogonal if and only if the row vectors form an orthonormal set. Or you could also say the column vectors form an orthonormal set. So maybe that's why they called this matrix orthogonal. Let's take a look at the row vectors. And we'll do this in a different color, maybe blue. So we're done with this problem, by the way. We're just investigating this theorem. The row vectors happen to be this. I'll write them like the ordered pairs. 1 over root 2, 1 over root 2. And then negative 1 over root 2, 1 over root 2. Is this an orthonormal set? Well, let's take the dot product. We get negative 1/2 plus 1/2. The dot product is 0. And we're just doing the regular, the standard inner product for R2. And each of those have length, each of those vectors have length 1. So this right here is an orthonormal set. We can do the same thing with the column vectors. Okay, so that's the first part of orthogonal matrices. Let's take a look at another example here. Okay, so this is example number 2. With example number 2, we have a 3 by 3 matrix, and what we're really going to get at on this 3 by 3 matrix is we're going to figure out the eigenvalue eigenvector pairs. Okay, what do you notice about this 3 by 3 matrix? There's some special property here. Well, this 3 by 3 matrix is symmetric. Symmetric matrices have very special properties. I'm going to show you that it's almost like we're cheating but this is a theorem. I'm going to show you the first 2 parts of a theorem here. If A is symmetric, like we have there, then the following things are true. A is non-defective or it is diagonalizable. Okay, so that's always going to be the case if you have a symmetric matrix. And then all the eigenvalues are real numbers, or we just say are real, which is good because, when we have those ones with imaginary eigenvalues, that was a pain, but that's going to be needed when we do applications that involve oscillations when we're doing differential equations. But right now, this is good. So we're just going to find some real valued eigenvalues. So we know that this thing's going to be non-defective, and we know the eigenvalues are going to be nice real numbers. So let's go ahead and I know there's no instructions here, but we're sort of exploring on this problem because we're going to find something pretty neat about those eigenvectors. Okay, so let's find the eigenvalues. To find the eigenvalues, I know you're getting sick of me doing this. You might pause the video and see if you can do this on your own. We write out the A minus lambda I matrix. So this is 1 minus lambda 2, 1. And then the next row, we're going to have a 2, 4 minus lambda. We have a 2, 1, 2, 1 minus lambda. Okay, then I'm going to go ahead and take the determinant of that matrix. That's going to give me the characteristic polynomial. I think I'll just go across the first row. 1 minus lambda is in the positive position. I'm going to actually skip writing a few things down. I'm going to go ahead and write out the minor here. So this is going to be lambda squared. And we have minus 4 lambda minus lambda, so this is minus 5 lambda. Plus 4. And then minus 4. Okay. 2 is in the negative position, so I'm going to go minus 2. And then I'm going to write out its minor. This is going to be 2 minus 2 lambda minus 2. And then 1 is in the positive position. Once again, if you've just lost touch of what's happening, I'm figuring out what the determinant of this is. And the minor of 1 is 4 AD minus BC, and then we have minus 4 plus lambda. So what do we have here? We have 1 minus lambda. Inside the parentheses, those 4's are out of there. And so I have a lambda squared minus 5 lambda. I can factor out a lambda here. So lambda minus 5. And over here we have minus 2. Those 2's are out of there. Actually, what I could do is this is actually 4 lambda. Okay, so plus 4 lambda. And then over here, those guys cancel, and I have plus lambda. Okay, so I'm going to factor a lambda out of these 3 terms. So I have lambda here. I'm going to multiply the 1 minus lambda times lambda minus 5. So this is going to give me lambda minus 5 minus lambda squared plus 5 lambda. And then this is plus 4 plus 1. So we have lambda here. And then we have, look at this right here. This is a negative 5 here. Positive 5 there. So this gives me negative lambda squared plus 6 lambda. I'm going to factor out a negative lambda, so now I have negative lambda squared out front, and then this is going to give me lambda minus 6. I'm going to set this thing equal to 0, and that's going to give me some eigenvalues. So my eigenvalues are lambda equals, I'll start off with the lambda equals 6. Lambda equals 6, which has algebraic multiplicity of 1, since there's a 1 up there. And then over here is lambda equals 0, which has an algebraic multiplicity of 2. Okay, now I'm going to go ahead and find the eigenvectors. Okay, so traditionally in this lecture I think I've been circling this in green. So I'll start with lambda equals 6. I'll leave some room to put the results up there. Lambda equals 6. A minus lambda I is I go ahead and put 6 into this matrix, so I have negative 5, 2, 1, 2, negative 2, 2, and then we have 1, 2, negative 5. What am I trying to find on this matrix? I'm trying to find the null space. So before I do that, before I put the zeros there, I'm going to try to reduce this matrix. I'm going to multiply. This is going to become my row 1. I'm going to multiply it by negative 2 and add it to row 2. So I have 1, 2, negative 5, 0. This is going to give me negative 6. And then we have positive 10 plus 2 is 12. And then I'm going to multiply row 3 by 5 and 0, and just put a 0 right there, and that's going to become row 3. So I have a 0. And then this is 10 plus 2 is 12. And then negative 25 plus 1 is negative 24. So this gives me the matrix 1, 2, negative 5, 0, 1, negative 2, 0, 0, 0. I'm trying to find the null space, so there's zeros there. I have 2 pivots. I'll call my variables x, y, and z. Bound, free. Z is t. Y is from the second row 2t. And from the first row, x, okay, so we have plus 2 times y, so plus 4t, minus 5t equals 0. So x is going to equal t. My eigenvectors are going to look like this. They're going to look like t, 1, 2, 1. T does not equal 0. I can see that the, so I'll put the information up here. My eigenvectors look like this. T, 1, 2, 1. T does not equal 0. And the geometric multiplicity on this one is 1. Let's go ahead and do lambda equals 0. I put lambda equals 0 in here, I just get matrix A. So let me just go ahead and write that up here. Lambda is 0. A minus lambda I is just matrix A. By the way, matrix A is 1, 2, 1, 2, 4, 2, 1, 2, 1. We can clearly see that we have rows that are multiples of each other. So when you reduce it, you get 1, 2, 1, and zeros everywhere else. What am I trying to find on this matrix? I'm trying to find the null space of A minus lambda I. I'll call my letters X, Y, and Z. I have only one pivot. Bound, free, free. Z is T. Y is S. And from the first equation, I get X equals negative 2S minus T. So I end up getting, I'll put my t's first here. So V is T. You can put your s's first. And so this gives me negative 1 and then 0, 1. And then we go with our s's, negative 2, 1, 0. So plus s, negative 2, 1, 0. Both s and t are not equal to 0, and the geometric multiplicity happens to be 2. There are 2 parameters. And so what I've done here on problem 2 is I've done the same skills that we've been doing in 7.1, 7.2. And by that one theorem I showed you, we can see clearly that A is non-defective. And what else can we see? We can see that all the eigenvalues are real. Look, 0, that's 6, I think. 6 and 0 are real numbers. So that is what we have. Okay, we're going to continue because you're like thinking to yourself, well, what are we doing new that's in this section? You'll see here. Let's see if I can. Oh, here it is. So this is the problem we just did. Find an orthogonal matrix S such that S transpose AS equals diag 006. Okay, so we have some explaining to do. On our last problem that we just did, A is non-defective. This is the same A that we're looking at here. I did not put that here, so what is A? A is a symmetric matrix. 1, 2, 1, 2, 4, 2, 1, 2, 1. We can also mention that A is diagonalizable. Okay, so we can diagonalize A, but I think we're going to explore a little more before we do that. Oh yeah, and also notice when I rewrote problem number 2, I actually put an S there and a T there instead of having them like I had here. That's not going to make a big difference. I'll just go with this one because they are the same eigenvectors. Okay, let's take a look at some vectors here. What I'm going to do is I'm going to call this vector 1, the negative 1, 0, 1. There's vector 1. I'll call this one vector 2. And I'll call 1, 2, 1 vector 3. Let's explore something here. Let's take a look at some dot products. V1, that's this guy right here, dot it with V3. That's what I wanted to show you. Well, what is it? Let's take the dot product. It is negative 1 plus 0 plus 1. So that is 0. Let's do the dot product of V2 and V3. So this is negative 2 plus 2 plus 0. So that's 0. Let's do the dot product of V1 and V2. V1, V2. We get 2 plus 0 plus 0. So that's 2. So what gives here? When you have a symmetric matrix, so this is symmetric, this is what will happen when you find the eigenvectors. That some of the eigenvectors from different eigenvalues will give you a dot product of 0. Okay, so why don't we go ahead and take a look at our statement here. So our theorem, you have a symmetric matrix, then that matrix is diagonalizable. All the eigenvalues are real, so we have that. If lambda 1 and lambda 2 are distinct eigenvalues, okay, so there's 2 different eigenvalues, and we have 2 different ones in our example, then their corresponding eigenvectors are orthogonal, and that's what we found out. Any eigenvector from lambda equals 0 is orthogonal to any eigenvector from lambda equals 6. And that's why we got those zeros there. Now, why did we get a 2 here? Because this is an eigenvector from lambda equals 0, dotted together with another eigenvector from lambda equals 0. It doesn't guarantee you that their dot product is 0. This theorem just says when you're taking the dot product of two different eigenvectors from two different eigenvalues. That is what number 3 says. A has a set of n orthonormal eigenvectors. Okay, so in our case we have a 3 by 3 matrix. We have a set of 3 orthonormal eigenvectors. Okay, and we don't have that yet because these guys do not have a dot product of 0. A can be diagonalized with an orthogonal matrix S. And that is what they're asking us to do. Find an orthogonal matrix S. So before, what it used to say is just find a matrix S such that S inverse AS equals diag 006. So this right here was just 7.3, and it was just diagonalizing any non-defective matrix, and you can do that. But we can find, this theorem says we can do this. We can find an orthogonal matrix where, I mean, sure, the blue would be the same, but remember, an orthogonal matrix, S transpose equals S inverse. So they're going to write the directions this way. So we have to find an orthogonal matrix where that will happen. Okay, so how are we going to do this? Well, let's just show you the rest of this. This is the last theorem of linear algebra. Okay, so A can be diagonalized with an orthogonal matrix S. That is, S inverse AS equals S. Transpose AS is diagonal. That is, S inverse AS equals S. Transpose AS equals this, where A is a 3 by 3 matrix. Okay, so what are we going to do here? So it's like 7.3, where we are going to find a matrix S and the matrix D. D is the diagonal matrix. But our matrix S has to be an orthogonal matrix. So what am I going to do? It would almost be an orthogonal matrix if those guys had a dot product of 0, but they don't. So what I have to do to these two vectors you are not going to like. I'm going to have to do the Gram-Schmidt process. So that is what I'm going to do on these two vectors. Okay, remember the Gram-Schmidt process is a twisting and turning of these vectors through linear combinations to get me a nice orthogonal set. Okay, so the Gram-Schmidt process. Let's go ahead and see if we can remember what the Gram-Schmidt process is. It says W1 equals V1 and W2 equals V2 minus the projection of V2 onto W1. Now we don't have to Gram-Schmidt all three of these because this guy's already orthogonal to any guy over here. So we just have to Gram-Schmidt these two guys, which is not that bad. We just have to do these calculations. And really, this first calculation isn't bad. W1 is V1, and so we know what that is. That is -1, 0, 1. So this right here is W1. W2 is, okay, so this is, we're using projection talk. Why don't we go ahead and write out the projection? So this is V2 minus, okay, so this is going to be V2 dot it with W1, going back to the definition of a projection, and then we have W1 dot it with itself on the bottom, and then we have W1 there. Remember I said that formed a gun. Okay, so there's the gun there. Okay, let's continue. So we're figuring out what W2 is. V2 happens to be this right here. -2, 1, 0. Minus a scalar over a scalar. So V2 dot it with W1. That's those guys dotted together, which we already did. So this top part is 2. W1, which is this guy dotted with itself, is 1 plus 0 plus 1, which is also 2. And then W1 is -1, 0, 1. So once again, what I'm doing right here is just a linear combination of these eigenvectors for lambda equals 0, which is going to give me another eigenvector of lambda equals 0. So I'm not escaping the eigenvectors. This is still going to be an eigenvector of your matrix, but with lambda equals 0. So let's continue with this. This is -2, 1, 0. And I'll distribute the negative sign, plus 1, 0, -1. And then what do we have? We have -1, 1, because we have -1, 1, and then -1. So this is what W2 equals. Let's kind of circle these things so they're a little more in bold. We have that right there. We have W1 right there. And why don't we go ahead and circle this guy right here. So now we can see this guy right here, W2, is still an eigenvector of matrix A with eigenvalue 0. If you dot those together, what the Gram-Schmidt process guarantees is the dot product will be 0. And you got 1 plus 0 minus 1. So those guys dotted together give you 0. And we already know that this guy, who is V1 dotted with V3 is 0. But let's see if this guy dotted with V3 is 0. It should be, because he's an eigenvector with lambda equals 0. And look what we end up getting when we do the dot product. We end up getting -1 plus 2 minus 1. So these three vectors here that I have circled, let's just write them out here. V3, W1, W2 happen to be orthogonal set of vectors, and they're eigenvectors. So let's go ahead and see if we can write the answer. And I'm going to show you what some people do on the exam, so you got to make sure that you do not do this. So on the exam, this is what some people do. Let's see if I got a piece of paper here. They go, oh, we can do this now. Okay, so what were we asked to do? Find a matrix S so that this happens. So let me just write this down. So this is S transpose A S equals diag 0, 0, 6. So I'll do this in red, and we'll even put an X through this. So some people say, oh, well, what we're trying to do is find a matrix S, an orthogonal matrix S, such that this happens. And what these people will do is, and I probably would have done this too, especially if I didn't do my homework. I would say, okay, so two eigenvectors that are associated with 0, well, we're not going to pick those original two, but we're going to pick these two. And so I'll go -1, 0, -1, 0, 1, which is that guy, and then -1, 1, -1. So -1, 1, -1, and then this one is 1, 2, 1, 1, 2, 1. And then people would say, okay, there's the answer. There's my orthogonal matrix. But S, this guy right here, is not orthogonal I'll just say not orthogonal matrix. And remember, one of our properties, or it was from a theorem, it says the row vectors form an orthonormal set, or the column vectors do. But if this was an orthonormal set, these rows here, or these columns, let's just take a look at the columns. Let's focus on the columns. Then each of these vectors would have length 1. And we know the vector, you know, W1, that does not have length 1. So what do you have to do with each of these 3 vectors? You've got to normalize them. Okay, divide each of them by their length. And so instead of writing -1, 0, 1, here's the correct answer. The correct answer, well, what is the length of -1, 0, 1? Doesn't that have length? Let's put it over here. That has length √2, so you've got to go like that. That happens to be your first column, not -1, 0, 1. But it's kind of hard to put it like that here in the matrix, so you have to go like this. You have to go -1 over √2, 0 over √2, which is just 0, and then 1 over √2. And so this vector here, -1, 1, -1, this is actually the third part of the Gram-Schmidt process, is to normalize your vectors. Well, that now will have, that has length, well, let's see, that has length √3, so I'm going to divide each of these elements by √3. So this is -1 over √3, 1 over √3, and then -1 over √3. And then the same with this one right here. The length of this guy, this vector 1, 2, 1, happens to be √6. So I have 1 over √6, 2 over √6, 1 over √6. You do have to put them in the right order, because this right here is an eigenvector. You know, that's also an eigenvector, but this is an eigenvector for lambda equals 6, as you can see. So 1, 2, 1, and then we just normalized it. And then these guys right here are eigenvectors for lambda equals 0. So this guy right here, S, is an orthogonal matrix. I said we would put an X through this. We don't want to see you stopping there on the exam. We want you to write out the orthogonal matrix. So this matrix has the property where S inverse equals S transpose. And we have that written there. So that's what they're going to ask you to do in your homework. Let's show you the last piece of paper that I'm going to do with this. So you're not going to get one this bad in your homework. You're not going to get a 9 by 9 matrix. But suppose you had a 9 by 9 matrix. We have this right here. A is symmetric. And you will get, well, you'll see that A is non-defective. And you'll get these eigenvalues that are real numbers. And maybe this eigenvalue here yields 3 eigenvectors, independent eigenvectors, and this one 2, and this one 4. Well, because A is symmetric, anybody over here, dot it with any of the other guys, will give you a dot product 0. So like V2 dot it with V8 is 0, and V3 dot it with V5 is 0. It's when you start dotting the guys within these circles, you're not going to necessarily get a dot product of 0. So if you had to do a problem that was this bad, and you will not have to in your homework, the Gram-Schmidt process, you would have to do the Gram-Schmidt process just within each eigenspace. So you would do the Gram-Schmidt process with these 3 vectors. And then you would do the Gram-Schmidt process with those 2 vectors. Independent of this, you wouldn't be looking at those when you did that. And then you would do the Gram-Schmidt process with those 4 vectors. And we've never done in Gram-Schmidt with 4. So some people are under the impression that if you Gram-Schmidt all 9 of these in the process, you know, in one swoop, that will do the job, but you'll end up getting vectors that are not even eigenvectors of the matrix anymore. So you would have, so this one would need, you'd have to Gram-Schmidt those guys, do a separate Gram-Schmidt for those guys, and a separate Gram-Schmidt for those guys there. If A is not symmetric, then we have no hope orthogonalizing eigenvectors within each eigenspace. So this section, 7.5, it's only going to be for symmetric matrices. When you look at your homework problems, they will be symmetric matrices. An application I can think of this is rotation of a conic. So we're not really going to get into that because it would take a lot of time to learn how to apply this to rotate a conic section. This is it for linear algebra. Everything else we do in this class will be differential equations, and we will see a lot of this linear algebra help us with differential equations. Do your homework. Have a good day. See you in the next video.